Hello, welcome to our lecture today on research methods in cognition. Hopefully this one will work. This is the third time I've tried to record this, so let's hope the third time's a charm. Today we're going to be talking about is basic research methodology in cognitive psychology. We're going to talk a little bit about scientific method, talk about experiments, correlational designs, quasi-experimental designs, etc. So here's what we'll do. We're going to start off with a review of scientific method, talk a little bit about psychological measurement, do an intro to experimental psychology, and then talk about cognition in the real world with some brief discussion of correlations and quasi-experimental designs. So first, we'll do a quick review of scientific methodology. We'll talk about how science is an epistemology, talk about why science is the best epistemology for cognitive psychology, a little discussion of scientific method, and a little discussion of what are good scientific theories. So science is an epistemology, and an epistemology is simply a way of knowing. How do I know something to be true? How do I gain knowledge? How do I gain truth? So this is how we know things to be true. Science is a combination of other classical epistemologies. So science is an epistemological method. It's a way that we learn and gain truth, but it's based on some classic epistemologies. First of these is rationalism, and rationalism is simply gaining knowledge or gaining truth or knowing through logic. The classic sort of rationalist example is René Descartes in his very famous Cogito ergo sum, in which he was trying to decide whether or not he existed, and he was trying to determine whether or not he existed through purely rationalistic methods. And so he thought, in order to think, I must exist. Because I can think, I must exist. I think, therefore I am, which is what cogito ergo sum means. So that's a basic rationalist position. And rationalism is incredibly important to science. All scientific theories are rational, or should be. They're based on logic, but I refer to rationalism as being necessary but not sufficient for full scientific explanation. We have to add to it empiricism as well. And empiricism is a philosophical tradition in which we know or gain truth through direct experience or observation. And so an empirical method is one in which we directly observe phenomena and gain truth that way. So rather than through pure logic, we gain knowledge through experience and through direct observation. Science is based in both empiricism and rationalism, so it is a systematic form of empiricism with rationalism at its core. Scientists aren't much on the classical authority epistemology, but we do rely on authority a bit. The classic example of authority is, of course, religion, in which all truth is gained by being told what is true through religious texts or from religious authorities. Scientists use authority in a different way, in that we rely on one another to accurately and fully explain our methods and our results, and we rely on scientific journals to vet those scientific procedures as being appropriate and their conclusions being appropriate. So a lot of truth comes from things like peer-reviewed journals, and so those are the authority in science. Underlying those, of course, are empirical and rational methodologies that allow something to be published in a scientific journal, which then gives it that authority. Scientists also do use our intuition, but not without backing it up without data. So intuition untested is hardly worthwhile. And so we use our intuition to think about how we think things are going to come out, but we back that up with data. So why is science the best epistemology for cognitive psychology? Well, this is where our intuition really goes awry. We are terrible at understanding our own cognitive abilities. In fact, most of our intuition about our cognitive abilities is wrong. For example, a lot of people believe that cramming for exams or repeatedly reading notes and repeatedly reading texts is an appropriate study tool for getting ready for an exam, when in fact it's the least effective form of studying. Repetition and basic cramming for exams is one of the worst ways in which we can actually long-term learn material. And so it's just a simple example of how our own intuition about how our cognitive functioning works is almost always wrong. We therefore have to conduct systematic tests to see how things work. So we gather data, we try to figure out what really is the best way for studying for an exam, what's the best way to teach, what's the best way to get people to learn. And of course, in this course, we've seen that one of the best ways to learn is through retrieval practice or quizzing. And this is where one of the biggest problems we run into is that authority often pushes their own intuition as policy. Oftentimes we see people will make policy based on what they believe to be true, and so you get educational policy, for example, that is based on people's intuitions about how people learn, when the data tell us so much more about how people actually learn. A good example of this are learning styles. There's this belief out there that people have different learning styles. That is not based on any scientific data, and in fact, there is no data supporting the idea that there are different learning styles. There may be different learning preferences, but there are not different learning styles. So this gets us then to the scientific method. And the scientific method is simply the systematic observation, measurement, and experimentation used in the formulation, testing, and modification of hypotheses. You've learned about the scientific method, I know, since you were in middle school at the very least. And basically, we use experiments that are specifically designed to test hypotheses that are all based in theory. So this is the systematic observation, measurement, and experimentation used in the formulation, testing, and modification of hypotheses. So it looks something like this. We make observations, we think of interesting questions, based on those we formulate hypotheses, we then develop testable predictions, we gather data to test those predictions, that data either supports, or we have to go back and refine, alter, expand, or reject our hypotheses and develop new testable predictions until we get it right, and then we develop general theories. Based on that general theory, we make more observations, we think of more interesting questions, we formulate more testable hypotheses, develop testable predictions, see how those predictions relate back to our theory. Scientific theories are a unique type of theory. They explain all available data through integrated sets of principles and will also organize and predict behaviors and events. Theoretical scientific papers are often very dense and very long because they're trying to integrate large sets of data into organized principles, integrating them all together, integrating all that data together, organizing it, and then predicting future events and behaviors. So when we're talking about a scientific theory about something like memory, it should predict how people will perform in experiments that haven't been done yet. So it should be able to help predict us, help us to define how memory will perform, people's memory will perform under circumstances we haven't seen yet, because we want it to be able to predict that kind of behavior. All theories should be falsifiable. That is, there should be a way to demonstrate that it's not true. So every scientific theory should be falsifiable. A bad theory is one that is not falsifiable, and generally these come under the rubric of things like psychic phenomenon. People will say, well, your negative attitude about my psychic abilities is limiting my psychic abilities, and so your testing of my abilities makes them not work, so that makes it not falsifiable. That is the idea that a skeptic is somewhere nearby, somehow interrupting the whole process, and as a result, you can no longer be psychic. Scientific theory should always be testable. One of the problems with Einstein's original theories is they weren't testable at the time. And so it took a long time for us to be able to actually test Einstein's theories. Once we developed technology, we've actually been able to demonstrate some of them to be true and some of them to not be true. All scientific theories should be parsimonious. That is, they should follow Occam's razor. That is, the simplest explanation is always preferred. We always prefer the simplest explanation because it is necessarily more likely to be true. Very simple way to put this is if one theory has 5 premises and another theory has 20, we randomly select one to be wrong, The one with 20 is more likely to be wrong. The simpler explanation is just by nature of mathematics, always more likely to be correct. Theory should also be specific. That is, they should really get as specific as possible in making predictions and explaining behavior. So the next general topic we'll discuss is psychological measurement. Psychological measurement is very different from other types of measurement because we are talking about dealing with people and trying to observe behavior that oftentimes isn't directly observable. Sometimes we have to infer that behavior. And so this is where we get into the importance of operational definitions. So when we talk about an operational definition, we're talking about providing very specific, clearly measurable, testable definitions of whatever constructs we're interested in studying. So for example, we might be interested in studying the effects of exercise on cognition in older adults. Great topic, plenty of people doing research in this area. But to do a research study, we have to do what's called operationalize. That is, we have to come up with operational definitions for those constructs. So we have 3 different constructs in that sentence to parse out. Older adults, cognition, and exercise. So we'll start with exercise. What do we mean by exercise? Well, for the purposes of this study, let's say we're going to do 30 minutes of light cardiovascular exercise twice a week. So 1 hour of light cardiovascular exercise per week. We want to see what the effect of that is on cognition, which is the next thing we have to identify. So we're going to operationalize that as, say, performance on the operation span task, which is a measure of working memory. We think that maybe working memory is the most important part of cognition, so that's where we're going to start. And then finally, we want to think about what do we mean by an older adult. 45, 55, 65. In general, an older adult is at least over 55, if not over 60. 55 to 75 is generally the age range we would be looking at. Next thing we want to do is we want to know our variables. So in the study we were just talking about, we need to identify potential independent, dependent, and confounding variables as part of our operational definitions. So in the exercise, cognition, and older adult study, we want to identify potential independent and dependent variables as well as whatever confounding variables we want to try to limit. So in this case, the independent variable is, of course, whatever we are manipulating. In this case, it's going to be exercise. We'll also need some kind of control condition. So for our exercise group, we might have a second group that is doing pottery for 30 minutes twice a week. So they're in a group activity outside of their home, doing something that's just not as strenuous as, say, light cardiovascular exercise. Our dependent measure then, of course, will be that performance on the operation span task, which is a measure of working memory. And then we want to think about potential confounding variables, particularly if we're talking about doing 2 different groups. So we want to make sure we have equal numbers of males and females in both groups, that the mean age is similar across both groups. And then we also want to be very cautious. So depending on how long this study goes on, let's say it's 6 weeks of exercise versus pottery, and we lose half the group in the exercise class. Well, that means that our resulting sample is probably very different at the end than it was at the beginning. What is it about that group that is still in the study that is different about the people that when we started? And let's say we didn't lose anybody from the pottery group. That's going to tell us a lot about our manipulation, and that there may be something really different about the people we have in those different groups. One of the keys to psychological measurement is to focus on or understand validity and reliability. These are 2 really important concepts. Validity of a measure means that something is measuring what it's supposed to. The validity of an experimental design is that it's designed to test what it says it purports to test. Reliability refers to the fact that we get the same result reliably or over time. So we're talking about the reliability of a measure. We're talking about if I give you the Wechsler Adult Intelligence Scale today and I give it to you in a week, your score should be relatively the same, that it should be stable over time. If we're talking about the reliability of a finding, if I find a difference, if I find exercise affects the operation span task in older adults in one study, I should find it in another. And so we really want to be careful and make sure that we have good, reliable, and valid findings. Experimental psychology is the core of cognitive psychology, and the reason for that is we are able to make cause and effect relationship determinations. So if the idea behind an experiment is that if nothing is different in our experiment but our independent variable, everything else stays the same, and somehow there's a change, and then there's a change in our dependent variable, then it has to be due to that manipulation of the independent variable. So back to our older adults example, if we've done everything right, our groups are, we've controlled all of our confounding variables, we have very similar groups in our pottery and our exercise groups, and the exercise group improves 25% on the operation span task, we can be pretty confident it's due to that exercise. Now that's only if we've done things right. So a better design for that might be we cross people over to across conditions. So for the first 6 weeks, they're in the exercise class, and then another group is in the pottery class. We test their operation span, and then we switch them. One goes to the pottery class, and the other goes to the exercise class. Now, of course, we're going to have to make sure that they're not exercising more in that second phase, because it might be that they liked getting exercise, they felt better, and so they're going to want to go out and get exercise. There's lots of things that go into this that make it very difficult. So the key here is, of course, is the independent variable needs to be responsible. That is, that needs to be the causal factor. So we can determine causation if and only if the only difference across our conditions is that independent variable. And this is, of course, whatever we've manipulated. So there are things that we sometimes treat as quasi-independent variables like gender, but those are not genuine independent variables because we have not manipulated that particular finding. So dependent variables are whatever we're measuring. Important distinction about dependent variables is to make sure that you're talking about the measure and not the construct. So for example, we can talk about intelligence as a construct and a dependent variable as the performance on the Wechsler Adult Intelligence Scale, or the performance on Raven's progressive matrices as a test of fluid intelligence. Working memory is another construct. Performance on the operation span task, performance on the digit span task, performance on the reverse digit span task. These are dependent variables, whereas the construct might be working memory. The dependent variable is how we're going to measure that construct. Again, we establish causation by holding our everything constant but our independent variable, the only thing changing, and then we measure changes in the dependent variables, and then we can establish causation. One of the biggest problems is confounding variables interfere with the ability for our independent variable to explain some change in our dependent variable. So that's how confounds can mess up our causation argument. So confounds are another type of variable. Again, the confound interferes with the ability of our independent variable to explain a change in our dependent variable, because it might be the confound instead of our independent variable. So out in the real world, we oftentimes can't do highly controlled experiments, so we have to make inferences other ways. The easiest ways to do this is often to do correlations. Obviously, we cannot establish causation simply from a correlation, but if we have a good set of laboratory data demonstrating the causal effect of a variable, and we take it out into the real world and support it with a correlation, it's a perfectly acceptable way to do research. So for example, lots of laboratory data have established that retrieval-induced learning by providing testing is a particularly good memory strategy. We then go out into a classroom, give lots of quizzes, and then we correlate quiz performance on final grade performance, and we might see that there is a relationship there. And so because there's been good data from the lab, we can be more sure of the correlational data we have in the classroom. We can also try to tease apart more our correlations a little more tightly by doing multiple regression. And what multiple regression allows us to do is to account for other extraneous potential variables. So we might be able to use classroom attendance as a way to parse out the effects of quiz grades on performance. So if we can account for Students that were in class more, that might then have something to do, for example, with motivation. That is, the students that are motivated to do better are doing better on the quizzes and the final exam. If we can somehow account for that, then we can be more confident of the fact that it's our quizzes that are actually responsible for our increase in final grades. Finally, quasi-experimental designs are another great way to conduct studies out in the real world. There are a number of ways these are done. In an AB-AB design, we may introduce and remove a treatment of some kind. So, for example, we might, in an intro psych class, do baseline for exam 1, do weekly quizzes for exam 2, baseline for exam 3, weekly quizzes for exam 4, and see how that's affected performance on those different exams. Oftentimes we are kind of stuck doing non-random assignment. So, for example, you might have 2 different sections of intro psychology, and you will put weekly reading quizzes in one and weekly in-class quizzes in another, or weekly quizzes in one and weekly journal writing in another to see how they compare, or weekly assignments of some other kind. It's obviously non-random assignment because students have signed up for those classes on their own, and there may be some reason they've chosen one time or another. That would also be what we call a non-equivalent control group design. Sometimes we can do random assignment with non-equivalent control group, where we again have, say, 2 intro psych classes, and we randomly assign one group to be part of one condition and the other group to be another. Again, they're non-equivalent, but we've randomly assigned groups to be part of those different control groups. So that's a basic introduction to cognitive psychology research methods. We will be talking next about cognitive neuroscience.